Thanks, Sam. It's indeed a pleasure to be back here after many years. So I'm going to try to keep this short talk to about 45 minutes and give you an overview of some of the research that my students and myself have been involved in for the last few years. And as she mentioned, last summer I became department chair, and I learned several philosophical lessons in life. As a PhD student, you know, as Khuller said one day, you know more and more about less and less. As a chair of the department, you know less and less about more and more. So it's an interesting thing. Shift. Anyway, so let me talk. Some of this research started a long time ago, and I'm going to sort of try to cover three different topics and show you how they tie together. And in my mind, this convergence happened only much later, and not initially, until we started seeing the common lens in which to view all of these problems. And so I think once you have this viewpoint, there is still more interesting things to do. Okay. So let me start off with a very basic question that some of you might have seen before. This is covered typically in courses on scheduling theory or courses on approximation algorithms, which is a very, very basic and simple model, which is something known as the unrelated parallel machine scheduling problem. In this problem, basically, you have a collection of machines and you have a collection of jobs. And the goal is to somehow find a good schedule for these jobs and the machines. Now, these machines are not identical. And so there is a matrix, P matrix, which is the processing time of job J on machine I. So there's a Pij value, tells you how long it will take to run job J on machine I. And you could even say Pij is infinity if you want to disallow a job potentially being done on a machine. And the goal is to somehow assign all these jobs to machines and also keep the maximum load on any machine load. Right? So that's the goal. So for example, we might have a job G1, which has very different running times on different machines. So it takes running time 2 on machine M1, running time 4 on machine M2, and can't be done on M3, and so on, right? And so the question is, we want to assign this job, and we don't want to assign just one job, but we actually want to come up with an assignment of all of these jobs simultaneously, trying to somehow bound how big the load on the machine might be. So this, for example, a schedule with make span 4, and then here's another schedule for this collection of jobs with better make span, right? So just you have to come up with the assignment. Okay. So this problem has been studied for over 2 decades. The first paper that actually developed some interesting approximation algorithms for this problem, not surprisingly, it's Picard, was a classic paper by Lenstra, Schmoes, and Cardosh going back to 1990, where they essentially showed that you can formulate this problem as an integer program, look at a fractional relaxation, so rather than trying to find an integer optimum solution, you look for a fractional optimum solution. And there's a very simple, elegant rounding technique that they came up with, which shows you that the maximum load on any machine is at most 2t, assuming there is a solution where every machine has load at most t. Right? So this is something that many of you might be familiar with. And in the same paper, they also showed that there is a 1.5 lower bound on approximability on this problem. Right? So there's still a gap here, which is that maybe we can improve the approximation guarantee to 1.5, but no better. And then a few years later, in a Soda paper in 93, Schmoes and Cardosh studied a further sort of generalization of this problem, where along with the jobs that have to be assigned to machines, there is also sort of an assignment cost, Cij, which is the cost that you pay to put a job on a particular machine. And then you have some global budget C on how much money you are willing to spend for this assignment. And you want to do the same thing. You want to get an assignment which has very low make span value for all the machines. And then they showed that even that problem, this generalization is a 2 approximation of the make span, but you don't violate the cost budget at all. So if there is a schedule where the maximum load on any machine is T and the total cost of the assignment is C, you also find an assignment where the cost is at most C and the maximum load is at most T. Okay? So this is a classic problem, and some of the work that we are doing has to do with the generalization of this question. So here's one generalization that motivated us to think about the following question. So what if the machines are not free? So these machines, you can think of them as some spectrum of choices that you have that are available to you, but every machine has a cost. So you have to pay some money to buy the machine. Either you're building a data center and you want to decide which sort of machines to build to do your workload efficiently. So there's a cost, or the cost could be simply be used as the energy cost to activate a machine. The other machines are idle. Right? So there's now 2 or 3 different things going on. One is that you have to assign these jobs to these machines, same problem as before. But also every machine has a cost in itself. So you have a bunch of different options, and you want to decide which machine to buy. So formally, the question that we arrive at is you have machines with some costs, and then I give you a cost budget on how much money I'm willing to spend to buy a machine, right? And now I want to select some subset of machines with the properties that cost doesn't violate the budget. And then once I choose a set of machines, I'm back to the same problem. I have a fixed set of machines, and I want to somehow assign these jobs to the machines. Okay. This question makes sense? Okay.
Cj of buying mi? The cost Cj is for buying mi?
Yes, the cost now is on buying the machine. Okay.
Did you mean Ci or?
No, it's just Cj. It's the fixed cost to buy a machine. Once you buy a machine, then you can allow it to load the machine. The machines that you don't buy, their load has to be 0. You cannot assign any job there. Okay. So now this should also perhaps remind you of another problem. So not only does it generalize the problem I talked about, if you have an unbounded budget of the cost, then it's exactly the problem that we had before, but it also generalizes another classical problem known as set cover. So a quick recap of what is set cover. So set cover is a very elementary problem where you have sets. These are shown in this bipartite picture by these nodes on the right, and we have some elements, and then every set has a cost which we have to pay to buy the set. And now the goal is that, again, we have to buy some collection of sets, and then the edges now correspond to a membership of a job in the set. So I can set that Pij value as 1 and infinity if the element does not belong to the set. And now we want to choose some collection of sets and have the property that we can assign all of these jobs to the chosen sets. But now, in fact, I don't even constrain what the load on the machine is, right? So it's unbounded load. And that's, again, the set cover problem because the budget that you spend on buying is exactly the cost of the solution.
So actually, going back to Madhukur's question, so the costs depend upon, can you go back to the?
Sure.
So I think the confusion was there is C.
No, so it is not the gap model.
No, is it Cj for machine I, or is it Ci for machine?
Oh, sorry, it's for the machine. Oh, I see. So
I think it's Cj and machine, so the.
Yeah. Oh, I see. This is just Ci. Sorry, thanks for pointing. Yes, it's Ci for machine. Thanks. The cost is exactly the machine. Yeah, I understand. Okay, so this is again a classical problem which is studied for, since the early 70s, and the very simple greedy algorithms that give you all the order log approximation. With that, and those were studied for the unweighted case where every set has sort of cost 1, and there's an easy generalization to the weighted case where instead of just greedily picking the largest sets or the sets that have the largest number of uncovered elements, you can look at a ratio cost of how many more elements can I cover compared to the cost of the set. And you can still get like a log n approximation for this NP-hard problem that way. And what is interesting is that even though the approximation algorithm is extremely simple, there is also a matching lower bound in some sense which proves that there would be a certain complexity class collapse if there was an approximation algorithm with factor better than log n. So there's some evidence that log n may be the right answer for this problem. Okay, so now that you've seen these two problems, so we are back to the question of generalizing the unrelated parallel machine to this machine activation question, right? So the main result that we were able to show in this sort of paper in 2010 was that if there is a solution where you pay cost at most C to buy some set of machines with maximum load T, then we can actually find a solution with cost log n times the budget C and with maximum load at most 2T. Right? And in some sense, this log n term is unavoidable due to the set cover thing, and this is unavoidable due to the machine minimization problem, the UPM problem. Okay? So the paper actually has a bunch of separate different results, and let me talk about one of the very simplest algorithms. So we have two basic approaches. One of them is based on an LP rounding approach, which gives you slightly worse approximation guarantees, but the algorithm is much faster. So it solves a single linear program, and then does a randomized rounding of the linear program, and then shows that you can get some nice behavior with those properties. Okay, but the bounds are slightly worse. So what I'm going to show you today is a much simpler greedy algorithm, where the bounds are slightly better, but the algorithm is not going to be nearly as fast as solving a single linear program. Okay? So it's a greedy approach in some sense. What I'm saying is that the way to think about the problem is to think about the set cover greedy algorithm, which says that every step I want to somehow choose one set or one machine, and then I can ask the question, how beneficial is this choice? How much more can I do if I buy this machine? And again, look at the ratio cost of how much more you can do with a certain machine to the cost of the machine, and then greedily try to choose the set of machines. Okay? So that's the basic idea of this approach. Now, sorry, is there a question? So now, suppose I have already chosen some set of machines to open, right? So that's the set S, with the property that I don't want to assign more than T units of processing in a single machine. So this I can sort of think about as some integer program or a linear program to capture that constraint. And ideally, I want to now decide which new machine to open. So every machine I open has a cost, and there'll be some more jobs that I might be able to assign, right? But the problem is, in this problem, it's NP hard even to find one assignment, let alone find what is the value of a new machine. So what is the incremental benefit of opening a new machine mi? So that's an NP-hard problem. But what we're going to do is we're going to relax this function fs to simply think of a fractional schedule. Okay? So we can write a certain LP, which will define some variable which tells me how much of a job is processed. And then we can use that LP as an oracle to tell us how much more fractional jobs will we be able to process if I open this new machine. Right? So I might have 10,000 jobs that I want to do. I might say I've opened these 4 machines. They have a budget of T on each machine. And then I want to write a certain linear program that says fractionally how much each jobs can we do. We want to maximize that for this set of machines given a constraint in the load. And then for every unopened machine, we can try to ask the question, how much is the benefit of opening a certain machine, right? And how many more fractional jobs will I be able to assign if I open this new machine? And then at every step, we're just again going to use the ratio rule. So it turns out that you can use a classical result of Woolsey on the analysis of this general greedy framework using submodular functions, and this gives you a log n approximation the same way as simple. Except that here it takes a little bit of extra work to prove that this function is submodular. That was shown by Lisa Fleischer. There's a simpler proof in my work with Gianni. Okay. So that is the basic greedy approach. So we start off with the empty set of machines, and then incrementally, until I have assigned fractionally at least n minus 1 units of work, where n is the number of jobs that I want to do, at every step, we incrementally choose a machine with best ratio cost. We keep going until fractionally at least n minus 1 jobs are scheduled, right? And these are all being done with the assumption that the load on any machine can never cross this budget of T. And in the end, we're going to use the technique by Schmoes and Tardosh, which is a technique for converting fractional schedules to integer schedules, and then you pay a factor 2 in that conversion. So you get this nice log n bound on the cost, and you get the bound of 2T on the basement. Okay? So that's the basic idea. But this algorithm is not very practical, as I pointed out, because if you think about how you're going to implement this algorithm, at every step, you have to solve a separate linear program just to choose one new machine, right? So at least in trying to do some experiments related to this that I might mention at the end of the talk, we found that this approach is completely impractical even for medium-sized instances. It's just too slow to solve this. And there are various heuristics and tricks that you can do. This kind of question shows up, for example, in the analysis of social networks, where people are trying to do the spread of influence maximization. And again, there's this greedy step which has to do this incremental computation every step, makes it slow. And then a lot of researchers in the AI community, for example, have looked at heuristics and speeding up this computation. So a lot of those ideas might be applicable here to eventually give a faster algorithm. But the algorithm that runs a single linear program is certainly very fast. Okay. So I already mentioned this result, and I also wanted to say that there's a related problem, which is related. So this is a model where every machine, every job has a processing time pi, and every machine has a certain speed. And the processing time of the job just depends on the speed of the machine. So if there's a machine twice as fast, you can do the job in half the time, right? So in that problem where all these machines are related, but in some sense that's a simpler model because it allows you to run any job on any machine, as this machine has a speed. So in that problem, you can do much better. You can get a polynomial time approximation scheme, for example, that was first shown by Hongbaum and Schmoes in the 80s, and then subsequently the simpler proof by Epstein and Sgall, which also gives a polynomial approximation scheme, and we were able to extend the Epstein-Sgall framework to get a p-task for this problem with a budget on the cost that you want to spend on buying. So that sort of concludes the sort of first part of the talk that I wanted to talk about. So our motivation was sort of twofold. One was looking at the energy cost of buying machines when machines are not free, or just the energy cost or the actual cost of deciding I want to do this computation here or this computation here, and different vendors might charge you a different amount. Okay? So I'm going to move gears slightly and now talk about a completely unrelated problem,
so quick
which
question.
is something that we studied a decade ago. Yes?
So is T known in the previous case?
So we sort of assume that if there's a schedule with this budget T, so in some sense, whenever we solve an LP, we have to guess a T, and then if it says infeasible, then we know that no solution exists to that value of T. For example, even if all the machines are open.
So then you can do binary search.
Yes, correct. So there is this parameter T which has to be guessed, and that's there in all of the previous literature as well. Okay. So I'm going to go back to, again, a very simple problem, and the motivation for looking at this question on vertex cover with soft capacities was completely different. So our motivation for studying this problem had to do with some biological application. So let me briefly mention what is the vertex cover problem and then talk about this generalization. So vertex cover problem is a very simple graph problem. So forget what's written up there. So you have a graph, and you want to, the goal is to cover all the edges of the graph somehow. So I want to pick some nodes that cover all the edges. So that's the vertex cover problem, right? So for example, in that graph, if I pick the blue nodes, I should be able to cover all of the edges. This is the covering problem. Right? So a very simple covering problem, which is NP hard. There are lots of different ways of solving it, lots of 2 approximations, and so on and so forth. Right? So we were interested in a couple of generalizations of this problem. One is that, of course, the nodes have weights, which is there for the standard vertex cover problem as well. But in addition, we have a capacity constraint for every vertex. So if I pick a vertex, the degree of the vertex might be 500. But if its capacity is 100, then if I pick one copy of the node, I can only cover some subset of 100 edges incident on that node. I cannot cover all of the edges. Okay? But we can then pick a second copy of the node and cover 100 more edges and so on. Right? But you have to pay for the second copy. So Rafi Hassin was visiting for one time, and his student Inat Or was working in a biotech company, and there was actually a particular application there which had to do with testing the presence of some substances in a chemical, and they could do certain tests, and their tests involved picking this node which corresponds to something in the biochemistry experiment, and then you can test for various other substances, the coexistence of other substances, which are some set of edges hitting this node, and you sort of have to decide which collection of tests that you do, and then you can do a second test to test other edges and so on. Right? So this was their original question, and they were wondering whether or not we can design some algorithm for this generalization of vertex cover. Now, again, all of these are related to set cover because, after all, I'm trying to pick nodes to cover edges, which is like picking sets to cover elements, except that things are a little bit simpler here. Every element belongs to only 2 sets. So like in the vertex cover case, it's a special case of set cover. We can get factor 2 approximation, so you might hope that you can get a factor 2 approximation here as well. So the capacity of the node is unbounded, like I said, it's the standard vertex cover problem. So this problem, it turned out, actually has a couple of different ways of solving it. Right? So there is an LP rounding algorithm that that we came up with later on. Initially, it had a factor 4, and then using some more complex techniques, we were able to show that you can still match the bound of 2. But the simplest algorithm, in some sense, was based on a very simple primal dual framework. So we have to write a linear program formulation or an integer program formulation for the vertex cover problem. So it's a little bit different from the standard formulation that you might be used to seeing. So if you see there's a variable up there in the objective function, which is x sub v. So x sub v here models how many copies of vertex v do we want to choose. And then every time I pick a copy of the node, I have to pay the weight of the node. Okay. And now that we have these assignment variables, YEU plus YEV for every edge UV. So this edge, in some sense, has to decide which endpoint it wants to be assigned to. So the sum of those variables has to be at least 1. And then there's a certain capacity constraint which says that you cannot assign too many things. So if I pick xv copies of a node, I'm allowed to assign up to kv times xv edges incident on that node. And this says that if xv is 0 and I never chose any copy of this node, then I cannot assign anything there. So it's a very standard program, very similar to the vertex cover program, but this generalizes it naturally to deal with capacities. So we write the dual of this. And so now it's a very simple primal dual algorithm. There's a few tricks that happen here which don't happen, a few things that are needed. If you don't really care about the approximation guarantee, this will give you an approximation factor of 4 very easily, I believe, right? But there's some issues that happen. So for example, nodes, we are raising dual variables. This is something that will make sense to you if you're familiar with the primal dual schema. If you're not, that's fine. But as nodes are being chosen, lots of edges are incident on this node, and we decide to choose this node. We don't really decide how many copies of this node we want right now. So we just say all these edges are covered, and later on we'll figure out how many copies of this node we actually need. And the reason is that you don't want to over-open too many copies because we can't afford to pay for them. So what happens is that if a node is open and this edge is assigned here, suppose the other node that this edge is incident on never gets chosen, then in some sense we have some spare capacity to charge the dual variable for this edge. Right? If the other end gets chosen, actually we have to reassign this edge to the other side. And then there's some interesting case analysis that you have to do to analyze it. But in the end, it gives you the same bound of 2. So we can match the bound for the standard vertex cover problem for this more general problem. So, but now I want to show you something that we didn't really explicitly think about earlier, which is that I can think about this problem in a very similar framework that we had with jobs and machines. I can think of every edge that needs to be assigned as a node on the left side of a hypergraphs graph, and I can think of every machine on the right, which is the vertex. And then if I choose 3 copies of the vertex, it has some capacity. It's like picking 3 copies of a machine, and then I pay 3 times for it, and then I can assign jobs there, for example. Or we might say that I can only pick 1 copy of a vertex, for example. Right? So that is a more general problem with hard capacities. So So some interesting observations here. So like I just said, if I can only pick one copy of a node rather than as many copies as I want that happened in the previous problem, things become actually a bit more involved. So for example, a generalization of the problem that we studied is this vertex cover with hard capacities problem. Now this problem is interesting because it behaves in some very funny way. So if I have weights on the nodes, then it actually becomes set cover hard, which is somewhat strange because each edge is still incident on two nodes. So we still have that property which was very useful for the vertex cover 2 approximation compared to the log n guarantee. But here if I have weights on the nodes and I still want to assign all edges to nodes and have a hard capacity constraint in every node, this problem becomes set cover. Right? So you can't do anything better than log n. This was shown in a Fox paper by Chuzaman and Howard. Right? So that's a little bit depressing because you can't sort of have any hope of getting a constant approximation. But in the same paper, what they showed is that the unweighted problem behaves very differently. And that's interesting because for most of the graph problems, you don't see the separation between the weighted case and the unweighted case, right? So for most of the approximation algorithms, the best results for unweighted problems typically, not always, are sort of the same. Or you can take an algorithm for the unweighted case and massage it or generalize it to get the result for the weighted case. But here, there's this huge difference in behavior. So you get a 3 approximation for that problem. And the algorithm is somewhat involved. And I'll explain at least a couple of the central ideas behind their algorithm. And then in an ICAL paper, soon after their work, we were able to improve it to a 2 approximation, but that algorithm is really very messy, and I won't talk about it too much. So here's sort of the central idea behind the Chuzaman-Howard scheme. And I think this is interesting because it's a very simple process, but the analysis is somewhat complicated. So the basic approach is the same. To again write down some IP, which is going to capture the problem. I now have these variables xv for every node, which are 0 or 1. I can either choose a node or don't choose a node, and then we have some hard capacity constraint. And once you relax this and get a fractional solution, their central insight is very simple. It says that if you look at any edge, then one of the assignment variables, one of these two, has to have value at least half, right? Because this edge could be split fractionally. It could be assigned 0.6 to one side and 0.4 to the one side. But you can't assign it to 0.4 to both sides because it has to be assigned somewhere. Okay? So one of the endpoints has value at least half. So what they sort of show is that you sort of pick every vertex with probability twice xv. Right? Now the nodes are fractionally chosen to some extent. But that also tells you that if the xv value is at least 1/2, this node will be chosen for sure. Okay? If the xv value is less than 1/2, then this node may not be chosen. So there's sort of these two classes of nodes. Some nodes have xv value at least 1/2. Some nodes have value xv less than 1/2. The ones that have value at least 1/2 will all be chosen for sure. The ones that have value less than x half, there's this randomized process that will choose them. Right? Now we do know that every edge has at least one end on a node with value at least 1/2 that's chosen. But that doesn't necessarily mean that that node is going to have available capacity for you. Right? So you have sort of, this is still, you're not done yet. So you still have to, after that randomized process terminates, you still may have to choose more vertices to get a feasible solution at the end. But in some sense, what they are able to show is that the expected number of vertices that you have to add to convert this into a feasible solution is very low, because the probabilistic events work out in that way. Okay, so the analysis is really messy. So if you look at exactly this algorithm that I described, if I remember correctly, they get a bound of something like an 8 approximation, right? So it's not really a 2 approximation. And then you change the thresholds, and you change the parameters, then you can finally, with some more complicated analysis, convert it to a 3 approximation. And then there's even more complicated analysis, like almost 20 pages long in our paper, to convert it to a 2 approximation. But the basic takeaway idea is this very simple randomized process. So one of the other things that I wanted to mention is that their approach, strangely, does not generalize to multigraphs. So if there are multiple edges between pairs of nodes, the algorithmic process is the same, but there's no way to extend the analysis to that, right? And more importantly, there is no easy way to extend it to the case of hypergraphs, right? So all the stuff I told you earlier about vertex cover with soft capacities, there are very easy generalizations to hypergraph case. So if an edge is not incident just to 2 nodes, but is incident to, let's say, a subset of vertices, up to 10 vertices, then you can get a 10 approximation, right? So the size of the hyper edge, in some sense, is the approximate term in the approximation guarantee. So in Barna's thesis, we were able to show that you can get an order D approximation for this hard capacity problem hypergraphs if the edges of size at most D, and this analysis also extends to multigraphs. Okay? And it's a little bit more involved because not only do we have to consider the kind of fractional solution that they consider, but actually we have to analyze the structure of this fractional solution a little bit more deeply. So let me say just a few words about it, and then I'll again change gears to a different problem. The main idea here is that we have to look a little bit more closely at the fractional solution. And it turns out that maybe the next example will actually make it clear. We have to partition. So let's take up this example for a second. So here we're back to the same problem where we have edges that have to be assigned to vertices. And after you solve the LP, you get some strange fractional solution, right? These values tell you that this node was chosen to value 0.4, this node was chosen to value 0.9, and so on. And then these are the edges which are all fractionally assigned to these nodes. You somehow still have to convert this to an integral solution, and the question is how should we do that? So some of the things that you have to observe here is that for some edges, if you look at the top edge, for example, the assignment variable for that node, which is 0.55, matches exactly the xv variable for the corresponding vertex, right? So the two are the same. But they don't have to be. It could be smaller. Like if you look at some other nodes, this assignment variable is 0.45, but that node has value 0.6. And this separation actually becomes important when you try to do something like pick every node with probability xv, and then the capacity of the node is going to be kv, xv, and so on, or you'll get a capacity of kv, right? So I have a little example here to show you sort of what's going on. So dealing with the case when the assignment variable is actually equal to the xv value is much simpler. So here's a simple example, right? So suppose some node had fractional value 0.7 and it has capacity 6. So now notice that in the constraint, this is giving you a budget of something like 4.2 for assigning variables. And then there will be a whole bunch of edges incident on this node with different fractional values, but notice that the total budget is still 4.2. Some of these fractional values are exactly 0.7. They can't be more than 0.7 because that was a constraint in the program. But some of them are exactly 0.7 and some of them are smaller, right? But now if I end up choosing this node in my solution, I'm basically scaling it up and I'm willing to pay the penalty to go from 0.7 to 1. So I'm willing to pay that penalty, I scale it up. But the capacity I'm going to get is only 6. I'm not going to get more capacity. So notice that the number of edges incident on this node is a lot higher than 6. And I cannot assign all of them. But when I do the scaling, these guys which had the same value as that, they can scale up and be completely assigned, but I still have to worry about these. Right? So there's many messy details that you have to deal with. So, but the central idea was that you can look at the structure of the linear program and then use that in some way to help you do this rounding process. And the constants involved are large, and I'm sure much better algorithms will eventually be obtained. But this is that at least you were able to show that there is a constant approximation if you have constant size hyperedges. Okay. So now I'm going to change gears one more time and talk about a completely different problem. So one of the motivating reasons for looking at this hyperedge generalization of this problem was that in the machine activation problem, if you think about a very simple model like vertex cover, it says you have jobs and each job can only be assigned to these two machines. And then I have to decide which machines to activate, which is like choosing nodes to open, and then each node has some capacity, right? That's the bipartite picture I was showing you all along. But what if it's not 2, it's 3? That's what sort of the reason why we want to look at this hyperedge generalization, that each job may have more than 2 options of which machines can do this job. So it could be 3, 4, like you might have, for example, some data that this job needs to run. This data is replicated 4 times or is on 4 different machines in some data center, and you might say, well, I can assign this job to any of those 4 machines. But the number may not be 2. So that was one of the reasons why we were looking at the case where a job can be done on some constant number of machines. It's not an unbounded number, but it's not 2. And as we saw, it's actually pretty hard to deal with a case which is not 2, but a bigger number. But that's how led us to trying to at least study this basic question of how do we assign these edges to nodes in this hypergraph. Okay. So, and this is another quote that we read from a paper written by researchers at Intel, which had to do with batch scheduling algorithms on machines. So this batch scheduling concept, which I'll talk about next, is actually quite closely related to some of the things that you've seen so far. So you've seen this machine activation problem that I talked about. you've seen this Vertex component hypergraph and hard capacities problem. And then the third thing I'm going to talk about is batch scheduling. And the interesting thing about batch scheduling is that, so what does it do with batch scheduling? Batch scheduling says I have a bunch of jobs which I want to do. Jobs may have some constraints, release times, deadlines, and so on, and some processing time. And I want to do these jobs in batches. Now, traditionally, if you look at all of the scheduling literature, literally over the last 40 years of parallel machine scheduling, almost all of it assumes that the machines are always on, right? The machines are always available, and then they look at trying to optimize certain metrics from the jobs perspective. How do I assign these jobs to these machines in some intelligent way? But we assume the machines are always available to us, right? So even in batch scheduling, which is a problem that's been looked at, they are trying to map these jobs to batches on the machine, so you can do a bundle of jobs together on a machine, but they never care, for example, how many batches you create, right? So a simple example might be that my wife tells me, hey, I want a cup of tea, and I would say, well, I want some coffee in 15 minutes. If you're willing to wait, I'll go to the kitchen once and I'll make tea and coffee together, right? So that's exactly like a batch scheduling thing, where I can do 2 tasks at the same time, right? Rather than doing 2 tasks separately. If I did 2 tasks separately, that's 2 batches. If I delayed one job and I did it with the other job, that's 2 things happen simultaneously. But of course, I can't do an unbounded number of things, so that's the batch size constraint. So you want to somehow cluster jobs, if you will, and do them in a way that you don't do too many things at one time, but you also try to optimize how many batches you create. Okay? Any questions? This is a good time to stop and take questions, because I'm going to change gears to a different scheduling problem, right? So this is a good time to ask any questions if you have. Yeah?
What's the typical power usage for a machine running two jobs at once compared to one? I mean, if
this you guys should tell me the answer to these questions. I don't know. So I will give you one other example in a second, which doesn't have to do necessarily with machine minimization. But the idea is that, let's say, for example, you have a multi-core processor. You say, well, if this processor is powered, I can run up to a certain number of threads simultaneously. And my energy usage might not change too much whether I'm running 3 cores or I'm running 15, but I can't exceed the batch size, right? So this is a simple model, but our model is extremely simple. I don't know whether it models reality or not, but as you'll see, there are some other compelling reasons to study this kind of model as well that I'll get to in a second. So for the last one, this talk, I'm going to assume a very simple model where we have jobs. And in fact, here the resulting algorithm is also very, very simple, so I'll actually go over the entire algorithm in detail. So jobs have release times and deadlines. And in the general version, the jobs have some processing requirement with length, but we'll also be interested in the unit job case, and that most of our results are right now for the unit job case. And we're going to assume that this batching machine has the property that time is slotted. So in each slot, the machine is either active, it's awake, you're paying some energy cost, or it's inactive. But if the machine is active, you can schedule up to B jobs in this machine. Okay? That's the capacity of that batch. Okay? And the goal is simply to minimize my energy cost, which is the number of active slots. Now, people have looked at non-batching models where they've tried to find, so for example, the paper I can think of is a classical paper by Baptiste, where they tried to find a way to schedule jobs where if you schedule 2 jobs next to each other, then you sort of pay in some intuitive way to turn on the machine once, then you run these 2 jobs or 3 jobs in a cluster, then you turn the machine off, right? But if you separated these 3 jobs out into 3 separate slots which are not contiguous, then you may pay these different on-off cycles, right? But there's no batching allowed there. So they are just unit jobs that you want to schedule, and then there are some dynamic programming algorithms to find an optimal solution in those cases. But the running time of all of these dynamic programs is huge. We're talking about like n to the 5, n to the 6. So, but the problem is not NP hard. Can we solve optimally for running time?
So one thing that happens in practice is
yes,
machines are already doing other things.
Yes.
So they're running services or something.
Yeah.
Or doing some storage work.
Right.
And batch things are done in the gaps in some sense.
I understand.
So you may not always turn it off.
So what you're saying is that with every time slot, somebody might prescribe a non-uniform batch size. So if you go back, and I'll show you another picture which, so for example, if you again, you see the next picture, right? So again, you can think of doing these jobs as things on the left side that have to be assigned, except that now here I don't have machines, but each time slot in some sense intuitively is a machine. And what you're saying is that this capacity function can be non-uniform, right? But each time slot is a machine now, which if I pay for that machine intuitively, then I get up to some processing capability in that time slot. If I don't pay, it's 0, which is exactly the way in which I've been looking at all of these problems until now, right? But this particular algorithm that I'm going to talk about is a very simple algorithm, but there the batch size has to be uniform. It's not unbounded. But people have looked at the problem that you asked about, and I'm going to give a pointer to a reference in a second. But the running time is much higher. It's not a simple. It's a dynamic programming algorithm, but the running time is much higher. Okay. So here's a very simple instance of what is the kind of problem we're trying to solve. I have, let's say, unit jobs. I have a batch size of 3, which is uniform in this case. This is time in the x-axis, and I have to find some schedule for all of these jobs. And I want to minimize the active time. And you can also think of the active time as once you find a schedule, I want to make sure that at every time at most b jobs are being done, and the cost of the schedule is sort of the projection of the schedule on the x-axis, because that's the time for which the machine is active, whether it's running one job or b jobs, it doesn't matter. Okay? So for example, this particular schedule would have 4 active slots, as shown. Okay. So now going back to some of the motivation in the scheduling literature as to why people looked at batching problems, it had to do with these 2 applications. One has to do with ovens and one has to do with trucks. And the applications themselves are slightly different, and I'll explain why. So the trucking model, it's like saying I have some packages that I want to send out on this truck. The truck has a carrying capacity, and every trip is like a batch. So the jobs have, or the packages have arrived at some point, they have to be delivered by some deadline. And then I'm trying to minimize the number of truck trips. Or if you're somebody who's organizing a conference and you have to pick up these 300 people who are arriving at the airport, they're all arriving at different times, and you have a certain collection of vehicles, maybe of capacity 20 each, and you just try to minimize the number of trips you make to the airport, right? But you want to make sure that you pick up everybody and so on and so forth, right? So that's exactly the trucking model. And the oven model is slightly different, because the oven model sort of lets you pull these pizzas or whatever the guy is baking in and out of the oven, even though the oven has a capacity. So for example, I might start this job here, and this time as soon as it's released, the job is halfway done, and then I can start another job because my batch capacity is 2, right? And then this job ends, this pizza comes out, another pizza can go in, right? So these models behave a little bit differently. You can't do, once a truck is left, you can't, right, push another package through, right? So these models are slightly different, but they're both batching problems. Okay. So again, you can use Woolsey's greedy algorithm for the problem I just described and get a log n approximation for this problem, where in some sense the sets that you're choosing at every step are the time slots with some budget of the capacity, and Woolsey's greedy framework gives you a log n approximation. So there's an exact algorithm based on dynamic programming by Evan, Levy, Ravitch, Shivers, Sahar, Sridenko from 2008. This algorithm, if I remember correctly, can handle non-uniform batch size at every step. They actually converted to a computational geometry problem where they have these intervals, like in this picture, they have these intervals, and they want to stab every interval by this vertical stabber, and these stabbers have some capacity of how many intervals they can cover, right? But it's basically the same problem. So, but as you see, the running time is quite high. This is the running time of the algorithm. It's a dynamic programming algorithm. But that one, I believe, handles the case of non-uniform batch size. So one of the things that was sort of we were thinking about is that why isn't there a much faster algorithm? And this is joint work with Jessica Chang and Hal Gavassi. I give references on at the end of the talk. So the algorithm that we came up with, I'm going to describe to you next, is called lazy activation, right? Now this algorithm sort of comes in 2 phases. Let me, since I'm a little bit short on time, let me not go over the motivation behind phase 1. Maybe if we have time at the end, I can explain that to you. But phase 1 is something which does something very simple. It says that, suppose I have a collection of jobs that I need to do. So this is the window in which every job has to be done. It's the release time and deadline for the job. We have a batch size of 3. And now I'm going to look at all the jobs with a common deadline. Okay? So notice here that I have 5 jobs with this common deadline. The goal is that somehow we want the property that we never have more than b jobs with a common deadline. Okay? So that will be a useful property to us later. Right? So we want to somehow take any input instance which has arbitrary release times and deadlines, and then we somehow want to convert it to the property where at any deadline value I don't have more than b jobs. Okay? And that conversion process is very simple, because if you think about it, in this last time slot, I'm never going to be able to do more than b jobs anyway, right? So what we do is we have this very simple rule which scans the slots from right to left, and then decrements the deadlines in what we're calling these overloaded slots, where there are more than b jobs per deadline. And then I'm going to favor decrementing deadlines of jobs that are also released earlier, right? So in this particular example, I have 5 jobs, and I want only 3 of them to have that deadline. So these two jobs, notice, were released earlier. So you're going to adjust their deadlines like that. Okay? And in some sense, you haven't really made any mistakes because the optimal solution can't do more than B jobs. Anyway, you can argue by an exchange argument that this is the sort of right thing to do. It doesn't cost you anything to do that. And we do this recursively. So now what may happen is that you decrement the deadlines of these jobs. Now it may be that there are more than B jobs in this deadline. And so we're going to apply this rule recursively and then again do the same greedy choice to decrease the deadline and so on. And now you might wonder, what if some jobs window collapses to empty? So in that case, we can prove that the job sort of has no way to be done in any feasible schedule, basically, more or less. And even if you do that, and it just means there's no feasible schedule that does all the jobs. And in fact, we can also show that the number of jobs done is maximum possible. So it's not as if there would be another schedule that would do more jobs. Okay, so everything is hunky-dory so far, right? Now the algorithm after this pre-processing becomes extremely simple. So now I'm going to go to step 2 and order jobs in increasing deadline order. And you will see in a second why that property from step 1 will be useful. And let me explain the algorithm by an example. So I want to sort of focus on what is the job with the earliest deadline and worry about doing that job, right? So let me go to this example. So imagine that I've already done the pre-processing. So that was B jobs with any common deadline. Now look at the job with the first deadline. That's this job. This job has to be done somehow at some point of time. And there's no reason to do it too early. I will sort of intuitively maximize the overlap with other jobs if I delay it. So we will do it as late as possible. So we'll schedule that job there, right? So this slot will be active. And in some sense, you can prove that the optimum also has to, without loss of generality, activate this slot for this job, because the optimum activates the other slot. You can always change the optimum to do this. But now that I have some spare capacity here, right? Because I can do B minus 1 other jobs. And for those jobs, out of all the overlapping jobs, we'll simply pick the ones with the earliest deadlines. It's a very simple rule, right? So we'll keep doing this. So I can pick those jobs, then I remove them all from the instance, look at the job with the next deadline, schedule that, look at all the overlapping jobs, remove those, and keep going, right? And this algorithm, if you're very careful, you can actually even implement it in like basically linear time and get the optimum schedule. So for this example, the optimum schedule looks something like this. And let me skip the proof. So there's a few other things that I want to say. So this is okay. So let me say a few other words, which is we're also interested in a slightly more general model, which is that what if a job doesn't have a single window of time in which it has to be done, like a release time deadline, or maybe there's some disjoint collection of windows in which this job can be done, right? So that's another interesting problem. But turns out very quickly you sort of get NP hardness there. So this is a much harder problem, and the reason is that, for example, you can show that this model can be captured in the set cover framework, and all the standard NP hardness proofs go through, right? So this problem is a little bit more involved. But going back again to this bipartite graph or a network flow way of thinking about things, again, what we have here is a collection of jobs that somehow we want to assign to time slots, in this case, or machines. And then whenever I decide to activate a machine, I get a certain capacity of B, right? So those of you who are experts in network flows will notice that there is also a flow problem, which is very similar, called min edge cost flow, which is different from both max flow and min cost flow. So in min cost flow, you want to find a flow with certain value, and you pay like a linear function on every edge. So if you send 3 times the amount of flow on some edge, subject obviously to some capacity, you pay 3 times the cost. In min edge cost flow, it's sort of this binary function. So if you send any non-zero amount of flow on this edge, you pay a fixed cost, and then there's some capacity that you get. Okay? So a min edge cost flow is not surprisingly NP hard. There's some hardness of approximation results. But all of these problems, you can think of them in this way of min edge cost flow, where they have all these common properties. And we are being able to exploit certain properties in terms of deriving better approximation guarantees. Because min edge cost flow, the approximation results are basically all mostly hardness results. There are no interesting approximation algorithms for the most general problem. But here, sometimes we're able to exploit the property that each node here has low degree, for example. It has very few options, and that's useful. Or this batch size is uniform. Or the set of time slots you go to is a convex set. So you go because you have a release time and a deadline. So all of these special properties are sort of useful in trying to understand special cases of this problem. Going back to the problem where each job doesn't necessarily have a single release time and deadline, but possibly a set of possible time slots that can be done on. So we just have this arbitrary bipartite graph where an edge means this job can be done on this time slot and so on. This problem, the NP hardness proof, crucially used the fact that the B value, the batch size for that time slot, is greater than or equal to 3, right? So initially we didn't really think about what happens for the batch size 2. It turns out that the batch size 2 problem isn't NP hard. There is actually an optimal strategy that solves it. And the optimal strategy has to do with matching, and somewhat interesting, so let me talk about that a little bit. So this relates to a problem known as the maximum bounded degree subgraph problem. So the maximum bounded degree subgraph problem, you're given an arbitrary graph G, you have some upper bounds on the degree constraints of the nodes, and the goal is to find a maximum collection of edges, but that you don't violate any of the degree constraints, right? And this graph doesn't have to be a simple graph, I can even stick in cell groups. So we're going to create an instance of this maximum bounded degree subgraph where we have a degree bound of 1. In fact, I don't even have to set it exactly equal to 1. I can set it like at most 1. Equal to 1 makes things a little bit easier. And a degree bound of at most 2 for the time slot nodes. And the main property that I want to show you is something like this, which is that in some sense, every time a time slot is inactive, you sort of gain one self-loop. Okay? So for example, if you look at this schedule, the first 2 jobs are assigned to that common machine which has a capacity of 2. The third job is sitting all on its own, it goes there, these 2 jobs, right? So if you sort of split your jobs and spread them out and you don't utilize this batch capacity of 2, then none of the self-loops can be chosen, right? If I somehow have n jobs and n slots and I spread them out, then I cannot choose any of the self-loops because the degree constraint of at most 2, right? I assign one job here and there's a self-loop that can't be chosen because the degree. So if I choose a self-loop, it already increases the degree by 2. Right, so in some intuitive way, every time you pair up a set of jobs onto one machine, it lets you pick one more self-loop. So that's sort of the intuitive connection. The rest of it is all details. But the formal property that we have to argue is something like this. So as I already mentioned this problem, maximum degree subgraph, this problem itself in turn is solved by reducing to the bipartite matching problem. And there are actually reductions that even reduce it to bipartite matching. But like I said, it's a little bit more involved. So you have to first start off by finding a standard maximum matching without the self-loops, and then you have to sort of do the augmenting path tricks which are standard for matching, but after adding the self-loop, then ask the question, how many more edges can I add to this degree constraint subgraph? And in the end, the property you get is something like this, that the size or the number of edges in the degree constraint subgraph you can prove is exactly equal to the number of jobs, because in the initial step we matched all the jobs, we started out with a perfect matching for the jobs, plus the number of self-loops. Now the number of jobs is a fixed amount, so if I maximize this, I'm maximizing the number of self-loops, which is exactly like maximizing the number of inactive slots. So every time you have a self-loop, that node is inactive because there's no job assigned to it, basically. Okay. So that was one correction that I just wanted to talk about a little bit. We also looked at one other problem which has to do with the idea of having partially active slots. So let me just explain what the problem is. So here we have a batch size of 2, but notice that we don't necessarily, so we have 3 jobs here. The yellow job, I'm not sure what that color is, and this maroonish job, right? So we have 3 jobs. If I have a batch size of 2 in the normal model, I sort of need at least 2 active slots, right? In one slot I can do 2 jobs, and then in the second slot I can do 1 job, right? So, but now if time slots can be partially active, you can start doing strange things like I do this job from time 0 to time 1. This next job starts at time half and goes to 3/2. And then that first job is split up and it's done a little bit here and a little bit there. And now notice that at no point of time am I doing more than 2 jobs. But if I look at the projection of this schedule on the x-axis, it's only using time 1.5 slots, not 2 slots, right? So this is not a thing that we understand very well, other than the fact that it's clear that there are cases where you might have an instance where if you're not allowed to preempt, it costs you more than if you're allowed to preempt, right? So like here, I can reduce this 2 slots to 1.5 slots. And we were only able to analyze this for the batch size 2 case. So in the batch size 2 case, basically, the main thing that we can show is that that example I showed you is the worst thing that can happen. So in that example, the ratio of the non-preemptive schedule to the preemptive schedule is something like 4/3. And basically, that's the worst example. So the ratio is upper bounded by 4/3. And this proof is really quite involved. So I don't even know how to get started on the case when the batch size isn't 2. But our conjecture is that this bound here will be some function of the batch size b, but it will be something like 2 minus some 1 over b plus 1 or something like that is what we were projecting, but a little bit less than 2. So our conjecture is actually that this idea of preemption, even for large b, is not going to save you more than a factor of 2. It will give you some savings, but not a huge savings. But we don't know how to prove that yet. Okay. So I already, I think, have been sort of through the talk talking about this idea of this min edge cost flow problem. And for the most general problem, we don't really know how to solve it. And all the lazy activation and all this stuff I showed you is only really for the case of unit jobs. If the jobs are not unit length, then I don't really know how to solve this problem, right? So this is again a picture about what happens. So this is exactly like saying I want to maybe choose these 3 nodes and pay the cost of these edges in the min edge cost flow framework, and then gives me some budget of how much flow I want to send. And the goal is to route all of the flow subject to some constraint on the cost. Okay. So let me sort of conclude here by saying a few things about some open problems, right? So the first interesting question in my mind is whether or not there is a simple combinatorial approximation algorithm for the vertex cover with hard capacity. So everything that we did so far involves solving a single linear program, but the rounding process and the analysis is extremely messy and complicated. And I don't know whether or not it will be a simple approximation algorithm. Because for the standard vertex cover, there's literally a 3-line algorithm that gives you a 2 approximation. But of course, that's with unbounded capacities. Right? So whether or not it's a simple combinatorial algorithm that will deal with the capacity case, we don't know that. Right? And this active time scheduling problem that I talked about, we can only prove optimality for the unit job case. If jobs have arbitrary lengths and you want a non-preemptive schedule, then there's an easy proof that it's NP hard. Okay? But if you're allowed to preempt jobs, so I say that this job has some length of 5, right? This thing I have to do needs 5 hours of processing, but I can do 1 hour today, 1 hour tomorrow. It doesn't have to be necessarily in contiguous time slots. Then we actually don't know that the problem is NP or NP hard. Right? So it's an interesting question. And more recently with Jessica, we were looking at this min edge cost flow framework and also developed some alternate heuristics to the greedy approach based on eliminating slots rather than incrementally adding slots. And those heuristics actually behave quite well. And in a lot of test cases, give you extremely good solutions, like within +1 of optimality and so on. And more recently, there was a SOTA paper just, I guess this month, not even last month, which looks at some online variants of the kinds of questions that I talked about as well as RMM. Let me quickly conclude by just giving you a bunch of references. So the first 2 papers are research that my students and I have been involved in. So the scheduling problem I just talked about was a paper published in ESA with Jessica and Hal Gabo. I also mentioned this experimental work that we did in the LNX conference just, I guess, a couple of weeks ago with Jessica. And then I mentioned some other results, which were the hypergraph problem with hard capacities. This was work with PhD student Varna Saha, who graduated and went to AT&T Labs, and so on. So the first, I guess, 6 or 7 papers are papers that I've been working on. This paper is one with actually a high school student I've been working with, Frederick. He's been looking at batch scheduling and parallel machines. So that work is not published yet. And one of the things that we did there was there's several dynamic programming based algorithms for many of these problems, but all of them have very, very high running time, something like n to the 5, n to the 6, and so on. In fact, for one particular version, our running time was like n to the 8. And so Frederick and I were looking at the problem of batch scheduling with multiple machines, even not even one machine. So the exact problem, this model is something like if you have, like I mentioned this application earlier, you have an airport, people are arriving, you have a certain number of cars, each car has a capacity, and you want to schedule the pickups for all those people, and you're simply trying to minimize the number of batches, the number of trips that you make to the airport. But now you don't have one car like in the trucking model, but you have a set of 5 cars, 10 cars, whatever, that's a parameter. So that's the number of machines. And it turns out you actually do not need dynamic programming. So we have algorithms that are pretty efficient, running time like roughly a cube, and will find you an optimal schedule. So you don't, without using any dynamic programming. Okay? And the other papers here are most of the papers that I mentioned as being closely related work that, if you're interested in this topic, would be a good starting point. And I can give a copy of the slides to answer if you need this. So let me quickly conclude by thanking my collaborators. So Jian Li was a PhD student at Maryland who graduated in 2011, is now an assistant professor at Tsinghua University. Varna Saha graduated about the same time in 2011, is now at AT&T Labs. Jessica is currently doing her PhD formally at University of Washington, but she's actually been at Maryland for the last couple of years before she graduates. And also, a lot of the scheduling work was joint work with Hal Gabo, who's Professor Emeritus from the University of Colorado, but still amazingly active in his research. So I've been collaborating with him mostly long distance. Okay, so let me stop here and take questions.
question. So
Yes.
So in the batch scheduling version, so the way you formulated it, it's like a single machine version, right?
Yes, yes. That was a single machine problem, not multiple machines.
So do you have a sense about if you have multiple machines and you add some of the constraints, like in the gap problem or something like that, where not all jobs can be executed on all machines, but then you still want to, I don't know, you define a machine to be active if you're executing at least one job.
So the work with Frederick is the closest to what you asked about. So there we have M machines. The batch size is uniform for every machine. Jobs have release times and deadlines. And in fact, there we don't even assume that time is slotted. So release time can be 73.5 and deadline can be 79. But we do assume that all the jobs have the same duration, right? So you can think of it as either my release times and deadlines are integers and all jobs have processing time P, which is uniform, or you can scale things so that P is 1 and then you lose the release time deadline being on integer boundaries. So that's why the techniques change. In our proof, this slottedness of time is crucial. That's what gives a very fast algorithm. If time isn't slotted, then things become a little bit messier. And that happens even in classical work by Barbara Simmons, and I don't know how much you're familiar with the unit job model, which was very popular in the early 80s. There's a bunch of papers. And the same issues you run into when the release time is not slotted or not integer. So in that model, we cannot enforce a constraint that this individual doesn't want to go on this this van at all. So the assumption is that anybody can go on any van, but they have the release time and deadline, and we have a fixed number of vans, and we're trying to ask the question, can we schedule a pickup for everybody, minimizing the number of trips? So there is work on batch scheduling where they don't care how many trips were made, right? But we really want to look at this energy cost or the cost of schedule, where we want to minimize the number of trips. And so that N-cube algorithm sort of solves that. But the batch size is uniform across all machines, and jobs just have a release time and a deadline, and then they can be scheduled on any machine within that window. They can't specify which machine. But it's a very interesting question, like how can we handle that? I have no idea right now.
So what are your thoughts on when the job length is not unit? Is it tractable or?
So Jessica and I actually have been working on that problem for 6 months. And at this point, we're not sure whether it's NP hard or not. So we don't have any NP hardness proof. Whatever algorithms we have seem to end up giving you an approximation guarantee, right? So I don't want to claim any result because we don't have it yet, but we have an algorithm that currently we believe the right answer for this algorithm is a 2 approximation. So we have no examples where it will do worse than 2 times the optimum busy time. We think we can prove like factor 4, but nothing is written down, so it's not confirmed yet. I mean, there's still some lemmas to prove, but that look right. But I think for the same algorithm, the right answer is 2. We don't have the proof for 2 yet. I think we have it for 4. But again, I don't even know if the problem is NP hard. So the formal problem is simply every job has some integer processing requirement. And so it has to be scheduled, say, in 3 slots or 5 slots in some window of time. And then whenever a slot is active, it can be doing up to B different jobs, right? You can't be doing 15 units of the same job, but you can be doing up to 15 units or up to B units or up to B different jobs. And you can do one piece of them. And then the final cost of schedule is the projection of the x-axis. But now jobs are not unit length. And every extension that we tried in the lazy activation seems to fail. So we've tried many different variants of rules for dealing with non-unit length jobs, and they don't seem to work. And looking at the structure of the optimal solution, it seems highly non-trivial. Like, for example, in the unit job case, when we opened a slot, we were able to use some simple greedy rule to fill in more jobs just based on the deadline, right? And now the jobs that overlap this slot, the problem is that they have deadlines and they also have different processing times. And we cannot come up with one rule because the future determines sort of what is the right thing to do here. And there are different future scenarios that seem to show that the different rules will suggest what needs to be done. So at least our way of left to right processing won't work, right? So there has to be something clearly much more intelligent that decides what jobs to do. So it's a problem that we've sort of been stuck on for a while.
And you allow preemption there? So
Yes, yes. So you don't have to do things in a contiguous way. If you are not allowed preemption, then you can prove a set theory. If you have to sort of fit things contiguously, then set theory. But if you're allowed to do, so the preemptive model, you can think of it as a chain of unit jobs. That's really the right way to think about it. Right. I have some precedence constraints. So a job is like, A1, A2, A3 is job A, 3 units of the job. Job B is B1, B2, B3, B4, B5, 5 units of the job. But it has to be scheduled in a chain. That problem, we don't know what the right complexity is.
So yeah, so for the batch scheduling job, just to clarify, right now the optimal solution is for unit length jobs.
Yes.
And they have to be released at integral time
Yes,
jobs.
yes. So if the release times are arbitrary, then the algorithm is significantly slower. It's n cube. It's not like this fast n log n type algorithm.
But it's still.
It's polynomial. Yes. Yeah, but the algorithm is completely different, and in fact solves a much more general problem, that algorithm, where you have up to multiple machines, not even just one machine.
So the extension that you mentioned with your student Frederick, does
yes.
it handle arbitrary release times, or it's also integer?
No, arbitrary release times. But the jobs have the same length. But the release times deadlines don't have to have any. You can choose it as 73 or 9 or whatever. Doesn't matter.
I think with preemptions, maybe a better model is you allow preemption, but there is some cost of preemption. Then that may.
Yeah, so I wouldn't be surprised if people have looked at models where preemption has a cost. I'm not that familiar with that literature. So we were looking at this as scheduling unit chains of jobs, really, as opposed to a job. But they're equivalent, more or less. But you're absolutely right. If there's a cost of preemption, then things could behave in a completely different way. So with 2 other students, I've been working more recently on a different scheduling model, which has more to do with as the number of jobs that the processor is working on increase, so you're allowed to add jobs to a processor, but they're sort of doing equal sharing of the processor. So if I'm running one job, that job is running at 100% rate in some sense. If I am doing 2 jobs, then each one is getting 50%. If I'm doing 3 jobs, each one is getting 1/3. So you can just keep adding more and more jobs. And there's some interesting applications to that. So one application that we were looking at had to do with filling boats. So I guess this, I don't really go sailing, but there's some deck on which there's a pump which is giving gas to different boats or ships. And there's a certain number of docking stations where the boats arrive. And this pump is providing fuel at a certain rate. And when this boat docks, they assume that the fuel is sort of being equally split. So if they're filling up 3 boats, then each boat is filling up at this rate of 1/3. But the docking station allows for 4 more boats to show up. They can join, then each one is filling at 1/7 or whatever, right? So there are some interesting models. And then there is some overhead for switching. So if a boat has to leave and another boat has to come, there's a fixed delay. So there's some very interesting scheduling models that you run into. You want to do things like minimize weighted completion time and things like that. And so there's a lot of interesting things that happen in that particular setting. So there's no explicit cost for preemption, but in some sense you can add and remove things, but everybody else gets slowed down. Other questions?
Okay, cool. Thank you, Samir.
Okay. Thanks.